Hello everyone, thank you for watching my video today. In this video, we're going to talk about a couple different things. First of all, we're going to talk about taking second derivatives or third or fourth or fifth or whatever derivatives of parametric equations, but really we're just going to focus on second derivatives. And also we're going to talk about finding arc lengths of curves given by parametric equations. All right, so first of all, let's talk about second derivatives and third derivatives, but really, again, like I said, the only derivatives we really need are the first derivative and the second derivative, okay? So, how do you find the second derivative? We would take the first derivative, obviously, and take the derivative of that. So we take the derivative of the first derivative with respect to t and divide it by the original dx dt that we already had found earlier. So let's take a look at a couple of those and see how it works. Find the second derivative. All right, so we're first derivative, so dy dx is going to be equal to dy dt over dx dt. dy dt, we're going to need to do a product rule with that, so it's going to be first times derivative of the second plus second times derivative of the first, which is 1, over dx dt is just e to the t. Okay? Simplifying that, even though we always say don't simplify, but when you're taking a second derivative, it's a good idea to simplify. If we take out an e to the negative t, we're left with negative t plus 1, or 1 minus t, all over e to the t. Simplifying a little bit further, I could either move this down or move this up. It all depends. Do you want to use a product rule or a quotient rule on the next derivative? I want to use a product rule, so I'm going to move the denominator up, and this is going to become e to the negative 2t, 1 minus t. All right. Now, our second derivative. So d squared y over dx squared. It's going to be the derivative of the first derivative divided by dx dt. So dx dt, we already got that as e to the t. So the numerator is going to be the derivative of the first derivative. We're going to use another product rule for that. And that's going to be the first function times the derivative of the second function plus the second function times the derivative of the first function. All right? And that's the answer. The directions do say that we should simplify as well. So let's simplify what we can here. If we take out an e to the negative 2t, we're left with negative 1 plus minus 2 plus 2t over e to the t. So that's e to the negative 2t, 2t minus 3 over e to the t. And I can bring that to the denominator and make this 2t minus 3 over e to the 3t. Get rid of that negative exponent. All right, if you'd like to try one on your own, you can pause this video right now and try problem B. If not, you can follow along as we go through it now. Okay, so dy dx equals dy dt over dx dt. dy dt is, so it's going to use a little chain rule here. So dy dt is going to be 2 cosine 2t. The derivative of x is going to be negative sine of t. All right, so now the second derivative, so d squared y over dx squared, is going to be the derivative of this divided by dx dt. So dx dt, which is negative sine t. And we're going to need a numerator to be, we're going to use the quotient rule to find the numerator here. Okay, so the quotient rule says the denominator times the derivative of the numerator, so that's going to be negative 4 sine 2t minus the numerator times the derivative of the denominator, which is negative cosine t, all over the denominator squared, so sine squared of t. All right, so simplifying that, well, our denominator is just going to become negative sine cubed of t. That's easy enough. And in the numerator, let's see, we have 4 sine t sine 2t plus 2 cosine t cosine 2t. And that, pretty sure that's as far as we can go with that derivative. So there we have our second derivatives. All right, back to semester 1, finding slope and concavity, but now we're doing it in parametrics. For the given curve, find the slope and the concavity at the point 2, 3. All right, so the slope comes from the first derivative. So dy dx equals dy dt over dx dt. So that's going to be, if you think of this as t squared over 4 minus 1, it's going to be 2t over 4, so t over 2 minus 0, divided by 1/2 x to the negative 1/2. So you can write this as t over 2 over 1 over 2 root x. Sorry, root, oh, I'm putting x's there, t's. All right, then if you flip and multiply, this would be 2t root t over 2, which you can simplify even further to t to the 3/2. All right, so if we're going to find the slope at the point, what was the point again? 2, 3. We have to figure out what t would be when we do that. So we can set 2 equal to root t, and that would be t equals 4. Or you could set this equal to 3, but this is an easier one to solve. So t equals 4. So then my derivative would be 4 to the 3/2, or 8. So my slope is 8. All right, part 2, now taking the second derivative, d squared y over dx squared. So it's the derivative of the first derivative, which is 3/2 t to the 1/2 over 1 over 2 root t. So you can think of this as 3 root t over 2 times 2 root t over 1. That's 6 t over 2, or 3t. And then finally, the second derivative at 2, 3. So that's again when t equals 4. Would be 3 times 4, which is 12. So this would be concave up. Increasing and concave up. All right, number 3, we're talking about position of a particle. A particle moving along a curve in the xy plane is at position x, y at time t, where we have dx dt and dy dt given for t is greater than or equal to 0. At time t equals 1, the particle is at position 2, 5. Find the slope of the tangent line to the curve at 2, 5. So remember that slope is dy dt over dx dt. All right, so that's going to be, we already have these, arc sine e to the negative t squared over ln of t plus 1. So we're trying to put in a 2 comma 5 there, but we can't really put x and y in there. But luckily we know that 2, 5 is t equals 1. So all we're going to do is put t equals 1 into that. And that's something we can do in our calculator here. We're just going to type in arc sine of e to the negative 1 divided by ln of 2. All right, so sine inverse of e to the negative 1 divided by ln of 1 plus 1, or ln of 2, and we get 0.544. So our slope here, we should write it like this, dy dt over dx dt at t equals 1 is 0.544. Okay, question B, find the x-coordinate of position at the particle time t equals 3. So this is an accumulation function. We already have, at t equals 1, the x-coordinate is 2. So at 3, so if we want to find x of 3, it's going to be 2 plus the integral from 1 to 3 of dx dt dt. Right? We know what dx dt is. It's natural log of t plus 1, but you can write that down as well. Okay, so now back to our calculator. 2 plus the integral from 1 to 3. Now, I already had taken the liberty of putting these functions into x1t and y1t. You can use that as well, or you could just type it out here. ln of t plus 1. You can see I am in parametric mode on my calculator. And we should be getting 4.159. All right, parametric mode, if you go to a mode, parametric mode would be the next after function. Okay? Keep your calculators out and handy. We're going to need those again soon as we move on to our next topic. So that's the end of topic 9.2. Now on to topic 9.3. Now we've seen how parametric equations can be used to describe the path of a particle moving in its plane. Our next step is to develop a formula for determining the distance traveled by the particle along its path. Remember, this is the arc length formula from last chapter. Okay? However, if our curve is represented by parametric equations, we can do some simplification here. So dy dx, we can put that in dy dt over dx dt. Okay, get a common denominator, all while changing this to dt. Oops, that typo there. This should be dt. I'll make sure to fix that for you. Okay. And then we can, if we bring this inside in the root, okay, we can end up canceling out the denominator, and that's how we get here. And dx dt is basically just f prime, and dy dt is just g prime. So this is our formula for parametric arc length. That's what we're going to talk about on the next slide. Parametric arc length formula is right there. Okay? So, quick note, when applying the arc length formula to a curve, be sure that the curve is traced out only one time. Okay, if you do make it into calculus 3, that's a huge point of emphasis as well. These things can be traced out multiple times, so you want to make sure that it's only traced out one time around the curve, not twice or 3 times for that matter. Okay? All right, so then distance traveled, it's the same thing. It's, if you're talking about arc length, you're talking about the distance a particle would travel on the arc, so it's the same formula. So if the question says arc length or distance traveled, know that it's asking the same question. Okay? So let's move on to some practice problems. Example 1, finding arc length for a parametrically defined curve. So remember, we need the two derivatives here, right? So x prime would be 3t squared y prime would be 9t to the 7/2. Okay. So then our arc length is going to be the integral from 1 to 3, because that's our t values there. Big square root x of t squared plus, x prime of t squared plus y prime of t squared dt. And this is something you could do this by hand, but in the interest of time today, we're just going to go right through our calculator to solve this. So go ahead and bring your calculator back out. And we're going to do integral. We're going to wait for this add to go away. Integral from 1 to 3, square root of 3t squared squared plus 9t to the 3.5 squared dt. I think I might have opened up too many parentheses there. And I just deleted it all. Let's try that again. All right, the integral from 1 to 3, square root of 3t squared squared plus 9t to the 3.5 squared. Okay, and I am getting 279.984. All right, just double checking on my other calculator to make sure that I didn't type something in incorrectly on this iPad calculator. No, same answer. Okay, so 279.984 would be our arc length. All right, question 5, find distance traveled. So again, we know that just means the exact same thing, right? So a particle moving along a curve in the xy planes at position xy, dx dt and dy dt are given. Find distance traveled from the particle on a time interval 1 to 2. All right, so distance traveled, we'll call it distance. Just the integral from 1 to 2 of big square root dx dt squared plus dy dt squared dt. All right, be careful typing this one in. Let's take our time. Integral from 1 to 2, square root of tangent inverse of, I already know I got to put another parenthesis there. Tangent inverse e to the negative t squared plus 3t over 1 plus 4t to the third squared. 0.407 is our distance traveled. Just got to be careful typing that in, that's all. All right. Last theorem of the day here. Area of a surface of revolution. If a smooth curve C is given by the equations x and y such that C does not intersect itself in the interval a to b, the area S of the surface of revolution formed by revolving C around the coordinate axes is given by the following. If you revolve it around the x-axis, we basically do our arc length times g of t, which is y. If you revolve it on our y-axis, it's our arc length times f of t, which is x. So let's take a look at one last problem today. I got my calculator up here still. We're going to need that for our next problem probably. Actually, I might be able to do this one without a calculator. Let's see if we can. All right, let's see the arc of the circle. X squared plus y squared equals 9. From 3, 0 to 3 halves, 3 root 3 over 2 as shown in the figure below. Find the area of the surface formed by revolving C about the x-axis. All right, so you can see the general shape of the figure that we have there. So first of all, we should probably convert this into polar form. If you remember your formulas here for polar form, x would be r cosine and y would be r sine. So in this case, x of t would be 3 cosine and r would be y would be 3 sine t. So therefore, x prime, so remember we need the derivatives here, would be negative 3 sine t, and y prime would be positive 3 cosine t. Okay? To find the boundaries, we can set either the x's or the y's equal to our equations. It doesn't matter. I'm going to do the x's. So I'm going to set 3 equal to 3 cosine t. So 1 equals cosine t. And that happens when t equals 0. And I'm going to set 3 halves equal to 3 cosine t. So then 1 half equals cosine t. And that happens at pi over 3 first. Okay? So now our formula. Our surface area is going to equal 2 pi, integral from 0 to pi over 3, of, since we're revolving around the x-axis, right, the x-axis, that means we're going to use g of t, which is y, which is 3 sine t. Big square root, x prime squared plus y prime squared. So x prime squared would be 9 sine squared. Y prime squared would be 9 cosine squared dt. So I said we could do this without a calculator because we can do this without a calculator. All right, just doing some thinking here. This root would be root 9 times sine squared plus cosine squared. And sine squared plus cosine squared is just 1. So it's just root 9. So that's just 3. Right? So we have the square root of 9 sine squared plus 9 cosine squared becoming the square root of 9 times the square root of 1, which is just the square root of 9. So now I can rewrite this as 2 pi integral 0 to pi over 3. This is just 3, so it's 9 sine t dt, which I can go even further and do 18 pi 0 to pi over 3 integral of sine. Okay, and the integral of sine, we just know is negative cosine from 0 to pi over 3. We'll put pi over 3 into there. We should get 1/2, so it's negative 1/2. Cosine of 0 is 1, so it's 18 pi times negative 1/2 minus negative 1. So it's just 1/2 of that, which is 9 pi. Could we use a calculator for that? Sure. But why not when we can do it by hand? Okay? That will do it for our lesson today on topics 9.2 and 9.3. Thanks as always for checking out the video, and we'll see you again soon.